Hello everyone and welcome back. So today in this lecture I am going to discuss about cut vertex and cut edge in a graph. Now before I go into the concept of cut vertex, let me first tell you what happens actually when a vertex is deleted from any graph. So suppose this is your graph G and you wish to delete this vertex U. Remember, when you want to delete any vertex, then along with that vertex all the edges which are incident on that vertex are also deleted. So if you wish to remove the vertex U from this graph G, then not only the vertex U will be removed, but if there is any edge in the graph which is having U as its end point, that edge will also be deleted. Here as we can see, U, this vertex, is the end vertex of the edge Ux. It is also an end vertex of the edge Uy, and also it is an end vertex of the edge Uv. So if I wish to delete the vertex U, then along with the deletion of this vertex, these three edges will also be deleted, because an edge cannot exist without its endpoints. So if a vertex is deleted, its corresponding edges which are incident on that vertex will also get removed from the graph, and this is what you obtain the graph G minus U. We write it this way. Now suppose I want to delete the vertex Z from this graph. If Z is to be removed, then along with this vertex Z, the edges YZ, ZV and ZW should also be deleted, because they are having, each of these edges is having Z as its end point or end vertex. So when I delete the vertex Z, these three edges will also be removed, and this is the graph that I obtain by the deletion of the vertex Z. So just remember, whenever you delete a vertex, see if that vertex is an end vertex of any edge. If it is so, then that particular edge or those particular edges will also be deleted as soon as you delete the vertex. Come to this graph G. Suppose I want to delete the vertex A from this graph. This is the vertex A. Now I can see the vertex A is an end vertex of the edge AB. A is also an end vertex of the edge AD. So if I delete the vertex A, then these two edges will also be deleted, and I will be left with this particular graph as G minus A. Suppose I want to delete the vertex G from this graph. Here G is a pendant vertex. It is having an edge FG incident upon it. So as soon as I delete the vertex G, the edge FG will also be removed. So this is the graph G minus small g. Now suppose I want to delete the vertex H from this graph. Now H is a vertex which is here isolated. It is of degree 0, there is no edge incident upon it. So if this vertex is deleted, as I can see, H is not an end vertex of any edge in this graph. So deletion of H is not going to affect any edge. So here if I wish to delete the vertex H, then only the vertex H will be deleted, and this is the graph that you obtain G minus H. Okay. So you have to make sure the vertex you are deleting, if it is not having any edge incident upon it, then you delete the vertex only. If it has one or more edges incident upon it, then delete those edges along with that vertex. Now we come to the concept of cut vertex in a graph. The definition goes like this: a cut vertex in a graph G is a vertex whose deletion from the graph will increase the number of components in the graph. Let's see this with the help of an example first. This is the graph G, where we can see that the graph is a connected graph, hence the number of components in this graph is 1. Now my job is to find the cut vertices in the graph, that is to check for the existing vertices in the graph which of these are cut vertices and which of these are not cut vertices. So as per the definition, to check if a vertex is a cut vertex, what do I need to do? I need to check whether the number of components of the graph increase or not when that vertex is deleted. For example, suppose I want to see if the vertex P is a cut vertex or not in this graph. Then what will I do? I will construct the graph by deleting the vertex P. So if I delete the vertex P from here from this graph, then along with this vertex P, the edge Px will also be deleted, because P is an end point of this edge Px. So the graph G minus P will look like this. Okay, and how many components are there in the graph G minus P? I can see this resultant graph still is a connected graph, and the number of components still is 1. So originally the graph has one component, Now also after the deletion of the vertex P, the graph has one component only, so I can see the number of components has not increased. Therefore, the vertex P is not a cut vertex, because the definition of cut vertex is a vertex whose deletion will increase the number of components. Now, if the number of components do not increase by the deletion of a vertex, then that vertex is not a cut vertex. If the number of components will increase by its deletion, then the vertex will be called cut vertex. Okay. So, we can see that P is not a cut vertex here. Now, suppose I want to check whether the vertex Q is a cut vertex or not. To check for the vertex Q, I need to delete that vertex and count the number of components in the resultant graph. If I delete the vertex Q, along with Q, the edge Qx will also be deleted, and this will be the resultant graph, which is again a connected graph. Number of components in this graph is 1, and therefore the number of components has not increased. Therefore, the vertex Q is not a cut vertex. In a similar manner, you can check and see that none of these vertices P, Q, R, S, T, U, V, W, none of these is cut vertex. Why? Because if you delete any of these vertex, the resultant graph still contains one component, no increment in the number of components, hence it is not a cut vertex. Now, let us talk about the vertex X. What happens when the vertex X is deleted? So, let us check whether X is a cut vertex or not. So, I will delete the vertex X and I will count the number of components in the resultant graph. Now, if I delete the vertex X, as I can see, X here is endpoint of all of these edges. So, if I delete the vertex X, then all these edges will also be deleted. So, let us construct the graph G minus X, then X will be deleted and accordingly the edges are also gone. So, what we are left with, the resultant graph G minus X has 1, 2, 3, 4, 5, 6, 7, 8. 8 components in total, because each isolated vertex creates one component, right? So, the resultant graph now has 8 components. Originally the graph had one component. So, the number of components has now increased. Therefore, the vertex X, whose deletion has resulted in the increment in the number of components, is a cut vertex. So, your job would be to list down all the cut vertices in a given graph. So, in this given graph G, the only cut vertex is X and all the other vertices are not cut vertices. Okay. So, what you will do? You pick a vertex, delete the vertex, see if the number of components in the resultant graph has increased from the original graph. If yes, then the vertex that you have deleted is a cut vertex. If not, then it is not a cut vertex. Just remember, we individually check for each vertex whether it is cut vertex or not. Let us come to this example now. This is the graph G. My question is, list down all the cut vertices of this graph. So, first I will check for the vertex A. If you are to list down all the cut vertices, you need to check for each of the vertices in the graph. So, let us start with the vertex A. So, if I delete the vertex A, then along with the vertex A, these two edges will be deleted. This is the resultant graph G minus A. Originally, my graph was a connected graph with one component. Now, after deleting the vertex A, the resultant graph is also connected graph containing only one component. So, number of component has not increased. So, the vertex A is not a cut vertex. Now, to check whether B is a cut vertex or not, you need to go back to the original graph. So, you restore your graph. Now, you check for the vertex B. It is not that you are doing successive deletion of vertices. You are deleting only one vertex at a time and you are checking whether it is cut vertex or not. Okay. So, to check whether B is a cut vertex or not, go to the original graph. This is my graph G where you have only one component. Delete the vertex B, which you are trying to check whether it is cut vertex or not. So, along with the vertex B, these two edges BA and BC will also be deleted. The resultant graph will be G minus B, which is again connected graph with one component. So, number of components has not increased and therefore, the vertex B is not a cut vertex. Now, we have to check whether C is a cut vertex or not. So, I go back to my original graph and I delete the vertex C and hence these edges are also deleted. This is the resultant graph G minus C. Here I can see that when the vertex C is deleted, the number of components in the resultant graph is 2. This is one component, this is another component. Therefore, the number of components in the graph has increased. That means the vertex C is a cut vertex. Now, we will check for the vertex D. So, come to the original graph, delete the vertex D. Here I can see the resultant graph G minus D has one component, no increment in the number of components. So, D is not a cut vertex. And finally, we will check for the vertex E. So, restore your original graph, delete the vertex E. see the resultant graph, still it has one component only, no increment from the original graph, and therefore E is not a cut vertex. So here we can see the graph G has only one cut vertex, that is the vertex C. So I list down the cut vertices of this graph and it is the only vertex C. Let's come to this example. So individually let us check for every vertex in the graph whether it is cut vertex or not, and finally we will list down our set of vertices which are cut vertices. Now before that, note down how many components your original graph has. So here we can see the graph G has 1, 2 and 3. 3 components are there. Okay. So note down that first. The number of components in the original graph here is 3. Now we will delete one vertex at a time and we will check whether it is cut vertex or not. So let us start with the vertex A. A is deleted. This is the resultant graph that I get, G minus A, which has 1, 2, 3 components. So there is no increment in the number of components. So A is not a cut vertex. Next we will check for the vertex B. So B is deleted. This is the graph that we obtain, G minus B. Number of components are 1, 2, 3, 4. So number of components has increased. That means B is a cut vertex. So I note down the first cut vertex that we obtain, that is B. Then I come to my original graph. I will check for the vertex C. It is deleted. This is the resultant graph, G minus C. Number of components 1, 2, 3. So no increment. C is not a cut vertex. Now we will check for D. So D is deleted. This is G minus D graph. Number of components 1, 2, 3. No increment. So D is not a cut vertex. Next we will check for E. So I will delete the vertex E and the edge which is having E as endpoint. This is the graph G minus E that we have. Number of components 1, 2, 3. No increment. Therefore E is not a cut vertex. Next I will check for F. So I will delete the vertex F and the corresponding edges. Therefore this is the resultant graph G minus F having 4 components. There is an increment in the number of components. So F is cut vertex. So B and F are cut vertices. Now I will check for the vertex G. So G is deleted and this is the graph where we have 1, 2, 3 components. No increment. So G is not a cut vertex. Finally we will check for the last vertex H. So H is deleted and this is the resultant graph G minus H. Number of components 2. So there is decrement. Now you have to remember, decrement in the number of components does not indicate cut vertex. Okay. Only an increase in the number of components will indicate the vertex is a cut vertex. So here H is not a cut vertex, okay, because there is no increment in the number of components of the graph. So the only cut vertices in this graph G are B and F. So these are the cut vertices that I have listed, B and F. Come to this graph. It is a connected graph where the number of components is 1. Let's check for each vertex if it is a cut vertex or not, and we will list it down. So let's start with the vertex A. To check whether A is a cut vertex or not, I will delete the vertex A and in the resultant graph I will count the number of components. Here it is 1. So there is no increment in the number of components, that means A is not a cut vertex. Then to check for B, I restore my original graph G. I come to the original graph and then delete the vertex B. So B is deleted. This is the resultant graph. Number of components still 1. No increment. So B is not a cut vertex. Next for C. So I will delete the vertex C and the corresponding edges which are incident on C, and this is the resultant graph. I can see in this graph there are 2 components. So the number of components has increased. So C is a cut vertex. I will list down C in the list of cut vertices. Next I will check for D. So I delete the vertex D and the corresponding edges. This is the resultant graph G minus D where I can see there are 2 components. So number of components has increased. So D is a cut vertex. So I list here D. Next I will check for E in the original graph. So I come to the original graph and I delete the vertex E. I have 2 components in the resultant graph G minus E, 1, 2. 2 components. So there is increment in the number of components. So E is a cut vertex. So I list down E. Then I come to F. So F is deleted from the original graph and I can see this is the resultant graph G minus F having 1 component, no increment. So F is not cut vertex. Likewise, I will check for G. When G is deleted, this is the resultant graph and there is no increment in the number of components. It is still 1. So G is not a cut vertex. So the cut vertices of this graph are C, D and E. Next come to this complete graph K5. So K5 we know every complete graph is a connected graph. So here K5 is connected and it has only one component, as we can see here also. Now we have to list down the cut vertices of this graph. So let's start with the vertex A. Then if A is deleted, then these edges are all deleted accordingly, and we are left with this graph where we can see there is only one component. So no increment. So there is no increment in the number of components, so A is not a cut vertex. Next I will check for the vertex B. So I delete the vertex B from the original graph and I find out the resultant graph where I can see there is only one component, so no increment, and therefore B is not a cut vertex. Next I will check for C. C is deleted and number of components in the resultant graph is still 1, no increment, so C is not a cut vertex. Next I will check for D. So D is deleted and the corresponding edges which are incident on D are also deleted. This is the resultant graph, no increase in the number of components, still it is 1, so D is not a cut vertex. Next I will check for the vertex E. Here also I can see the resultant graph after deletion of the vertex E has one component and there is no increment in the number of components from the original graph, and therefore E is not a cut vertex. So basically here we can see none of the vertices of this graph is a cut vertex. In fact, you can remember this, that in a complete graph Kn there is no cut vertex. No complete graph Kn has a cut vertex. Okay. Now we are going to the concept of cut edge. So before that, let us discuss about what happens when an edge is deleted from a graph. Now see, when you have deleted a vertex in a graph, since edge cannot stand alone without its end vertices, so if vertex is deleted, we have to see if that vertex is end vertex of any edge, accordingly that edge will also lose its existence. But when you are talking about deletion of edge, since a vertex can stand alone without the help of any edge also, so deletion of an edge involves only the removal of that particular edge, nothing happens to the corresponding end vertices. So if in this graph, suppose I wish to delete the edge UV, then only this edge UV will be removed. See, nothing happened to the vertices U and V. So removal of an edge results in a graph in which only that edge gets removed or deleted, nothing happens to the vertices of the graph. For example, here in this graph, if I wish to delete the edge BD, then only the edge BD will be deleted and I will be left with G minus BD. Or if I want to delete the edge, suppose EF, then only the edge EF will be deleted, vertices will remain as it is, and this will be the graph G minus EF. So that is easy. When an edge is deleted, only the edge is deleted. Now comes the concept of cut edge in a graph. Just like the way we have defined cut vertex, the definition of cut edge also goes like a cut edge or bridge. Another name for cut edge is bridge. It is an edge in a graph whose deletion will increase the number of components. Same idea. So if a vertex deletion from a graph increases the number of components, then the vertex is cut vertex. Similarly, if the deletion of an edge from a graph increases the number of components, then that edge is called cut edge or bridge. So basically, increment in the number of components by the deletion will indicate the presence of cut vertex or cut edge, as the case may be. So let's come to the examples first. So here we are given a graph G, in which we can see it's a connected graph having only one component. My job here is to list down all the cut edges in the graph. That is, which of the edges present in the graph are cut edges and which are not. So for that, what we need to do is, to check whether an edge is cut edge or not, I need to delete that edge and I need to count the number of components in the resultant graph. If I see an increment, then that edge will be cut edge. If I don't see any increment, the edge will not be a cut edge. So I will check for every edge. So let's start with the edge PX. Is it a cut edge? To find it out, I need to delete the edge. So PX is deleted. What I am left with is the graph G minus PX. I can see in this resultant graph there are two components. This is one component, this is another component. So there are two components in the resultant graph obtained by the deletion of the edge PX. That means there is an increment in the number of components by the deletion of the edge PX, which indicates by the definition that PX is a cut edge. So I list down PX as cut edge. Next, to check whether QX is a cut edge or not, I need to go back to my original graph first and then I will delete that edge. So you will delete one edge at a time and you will check whether it is cut edge or not. So again, in a similar manner, to check whether the edge QX is cut edge or not, I will delete the edge. See, only the edge is deleted, nothing happens to the vertices, and in the resultant graph G minus QX, I can see there are two components. So there is increment in the number of components, so the edge QX is cut edge. So I list down QX here. Similarly, if you check for each of these edges XR, and then for the edge SX, then for the edge TX, then for UX, then for VX, and finally for WX, you will find each of these edge is a cut edge. For example, if I want to check for the edge UX whether it is cut edge or not, I will delete the edge. The resultant graph that I obtain G minus UX, I can see it has two components. This is one component, this is another component. So, the number of components has increased. You will find this for each of the edges in the graph. That means every edge in this graph is a cut edge. So, PX, QX, RX, SX, TX, UX, VX, WX. All of these edges are cut edges. Every edge in this graph is a cut edge. Let's go to the next example. Here in this graph we can see it's a connected graph with one component. Let's see which of these edges in the graph are cut edges. Let's start with the edge AB. So, the graph that I obtain after deletion of this edge AB is this graph, and I can see it has one component, it's a connected graph. So, number of components does not increase. So, the edge AB is not a cut edge. Next, I will check for the edge BC. So, I will delete the edge BC, and the resultant graph is a connected graph with one component, no increment, and therefore BC is not a cut edge. Next, I will check for AC. I will delete the edge AC, and I will see that the resultant graph has one component, no increment, so AC is not a cut edge. Similarly, you can check for the other remaining edges also. You will find none of the edges in the graph is a cut edge. So, here there is no cut edge. Let's go to the next example. Here we are having three components in the graph. To check for the existence of cut edges, let's check for every edge one by one. So, let's start with AB. So, I will draw the graph G minus AB, that is obtained by the removal of this edge AB, and the resultant graph I can see has three components only. So, there is no increment in the number of components. So, AB is not a cut edge. Similarly, if you check for BC or the edge AC, you will see these edges are not cut edges. Now, let's check for the edge BD. So, if BD is removed from the graph that I obtain is this one. Here I can see that the graph has 1, 2, 3, 4 components. So, there is an increment in the number of components. So, the edge BD is a cut edge. So, I list it down. BD is cut edge. Next, I have the edge EF. So, let's find out whether EF is cut edge or not. So, remove the edge and count the number of components. You have 4 components in the resultant graph after removal of EF. So, there is increment in the number of components. So, the edge EF is cut edge. So, I list down EF. Similarly, you can check for the edge FG also. If FG is deleted, then this is the graph that you obtain, and it has 4 components. Number of components will increase. So, FG is also cut edge. So, this graph has 3 cut edges: BD, EF and FG. Next, in this graph, originally the graph is a connected graph with one component. Let's check for cut edges. So, if AB is removed, then this edge is removed and you are left with only one component, no increment. So, AB is not cut edge. Next, I will check for the edge BC. So, BC is removed and I get this graph, one component, no increment, BC is not cut edge. Similarly, AC is also not a cut edge, you can check it yourself. Same thing you can check for EF, it is not a cut edge. FG, its removal will also not increase the number of components, so that is also not a cut edge. And you can check for EG, that is also not a cut edge. Now come to the edge CD. So if I remove the edge CD from the graph, this is what I obtain. And clearly I can see there are 2 components in the graph. So number of components has increased. So the edge CD is cut edge. So I list down CD as cut edge. Next, if you check for DE, then you can see for this edge also its removal will increase the number of components. There is 1 and 2 components. So there is increment in the number of components. So DE is also cut edge. So here in this graph you have only 2 cut edges, CD and DE. These are the cut edges only. Next, we have the complete graph K5, which is connected graph with one component. Now let's check if it has any cut edge or not. If yes, then which are the cut edges. So let's start with AB. So if I remove this edge AB from the graph, the resultant graph that I obtain is this graph, which has one component only, no increment, and therefore AB is not a cut edge. Similarly, if you check for BC, then removal of BC from the graph results in this particular graph, which is again connected with one component, so no increment, so BC is not a cut edge. In a similar manner, you can check for every edge present in the graph and you will find that there is no cut edge in this graph. Okay, so basically in K5 we will find no cut edge. Now there is a theory to find out at once whether any edge in the graph is cut edge or not. just looking to an edge in the graph, you can conclude whether it is cut edge or not. And for that we have a theorem. So you need to go through this theorem statement. It will help you to at once decide for an edge whether it is cut edge or not. The theorem statement is that an edge in a graph is cut edge if and only if it does not belong to any cycle. Meaning, in a graph, if you find an edge is part of some cycle in the graph, that edge is definitely not a cut edge. If you find the edge is not any part of any cycle in the graph, then it is definitely a cut edge. Let's see with the help of an example. Suppose you have this graph G. Here if you talk about the edge AC, you can see AC edge in this graph is not part of any cycle in the graph. That indicates by this theorem statement that AC is a cut edge. See, an edge is cut edge if and only if it does not belong to any cycle. So if an edge, for example AC here, it does not belong to any cycle, so it is cut edge. I am listing down the cut edges here. So AC is cut edge. See, I can just at once decide whether an edge is cut edge or not just by looking into it with the help of this particular theorem. Come to the edge BC, we can say BC edge is not part of any cycle, it is not an edge of any cycle in the graph. By the theorem statement, if it is not part of any cycle, it is cut edge. Let's come to CD. Here we can see CD, this edge does not come on any cycle, it is not a part of any cycle, it is not an edge on any cycle. Then by the theorem, it should also be a cut edge. Then for the edge DE, here we can see the edge DE is part of this cycle, DEFD, or we can see DE is also part of this cycle, this C4, DEGFD. Okay, so we can see that DE is part of some cycle, maybe one cycle or two cycles or many cycles, but it is part of some cycle. If it belongs to a cycle, then by the theorem statement, it is not a cut edge. For the similar reason, EG being part of a cycle is not a cut edge. GF being part of a cycle is not a cut edge. DF is also part of cycle, so it is not a cut edge. Similarly, EF is also part of cycle. See, EF is a part of this cycle or it is a part of this cycle. So, EF is also not a cut edge. So, in this graph, since these three edges are not belonging to any cycle, for that reason, we can at once say these three edges AC, BC and CD are cut edges. So, this is a theorem statement that will help you to identify whether an edge is cut edge or not. Along the similar line, you can also remember this property in a graph which will help you to at once decide whether some particular type of vertices are cut vertices or not. So, you just remember that a pendant vertex means a vertex whose degree is 1, only one edge is incident upon it. A pendant vertex is never a cut vertex. And if you see an isolated vertex, that is a vertex of degree 0 on which no edge is incident, that vertex is also never a cut vertex. So, this property basically will help you to identify some particular vertices and to at once conclude that they are not cut vertices. Which type of vertices? If you see pendant vertices or isolated vertices in the graph, you can at once conclude that they are not cut vertices. For example, this is my graph G suppose. Here I can see that A is pendant vertex because A has degree 1. Similarly, D is pendant vertex. Similarly, E is also pendant vertex and F is also pendant vertex. Now, by this property I can see from property 1 that pendant vertex is never cut vertex. So, A, D, E, F, these are not cut vertices. I can immediately answer this. Okay. Next, isolated. Here, do I have any isolated vertex? Yes, G is isolated vertex because degree of G is 0. So, it is an isolated vertex by the property 2, isolated vertex is never a cut vertex. So, G is also not a cut vertex. So, by this property, immediately I can conclude that A, D, E, F, G are not my cut vertices. None of these vertices is a cut vertex in the graph by this property. So, any isolated vertex or pendant vertex, if you find in a graph, at once you can say they are not cut vertices. And for the remaining vertices, you have to check in a similar manner as we have checked earlier. So, for the vertex B, we will check. Now, before that, let us see how many components the graph G has. So, G has 3 components. As I can see, there are 3 components in the graph G. Now, we will check whether B, the vertex, is a cut vertex or not. So, I will draw the graph for G minus B. So, I will remove the vertex B. So, this is the graph that I obtained after removal of the vertex B, and I can see there are 4 components in the graph. So, the number of components has increased. So, B is a cut vertex in the graph. Okay. Let me erase down here. So, B is a cut vertex. Now, we will check for C. So, C will be removed and we will observe the resultant graph. We can see the resultant graph has 4 components. So, the number of components has increased. So, C is a cut vertex. So, in this graph G, there are 2 cut vertices B and C. Now, I am posting here few problems for your practice. The first question is, you are given a graph G and your job is to find out or list down all the cut vertices and cut edges present in this graph. So, you check for every vertex whether it is cut vertex or not and list down all the cut vertices, and then you check for every edge and list down all the cut edges. Okay. In the graph, if you find any pendant or isolated vertex, you can at once say that it is not a cut vertex, and for the remaining vertices which are not pendant or not isolated, you check individually. And for cut edge, only those edges which are not part of any cycle are cut edges, and if you find any edge which is part of cycle, definitely it is not a cut edge. So, follow the theorem statements and you utilize those to answer these questions. In the next question, we have been asked to find all the cut vertices and cut edges of the Peterson graph. So, we have discussed Peterson graph already in some previous lecture. So, you draw the Peterson graph, label the vertices, and you list down all the cut vertices and cut edges that are present in that graph. So, that is all for today. I hope you have understood the concept of cut vertex and cut edge from today's lecture. Still, if you have any doubt, you can always write to us in the comment section below. We will definitely try to sort out your problems. I am going to meet you again soon with the next lecture of this series. Till then, thanks for watching, and if you loved learning with me, then please do like, share and subscribe to our channel. Till then, take care. Bye-bye.